Hello and good morning. This is Mehek Arora and welcome to the third session of chemical equations. Before we go on to what we would be studying in this session, let us first recall what we studied in the previous session. We studied that law of conservation of mass dictates that all chemical equations be balanced. It means that the number of atoms of each element on the reactant side must be same as the number of atoms of each element on the product side. Why? Because in a chemical reaction, you cannot either create mass nor neither can you destroy mass. Before balancing chemical equations, we come to writing chemical formulae, and before that we come to understanding the concept of valency. It is the combining capacity of an element. Generally, we judge it by the amount of electrons an atom can lose or by the amount of electrons an atom can gain. Elements can either be monovalent, divalent, trivalent, or even variable valent. It means when an electron is either lost or gained by an atom, only one, then that atom turns into an ion and it is known as a monovalent ion. When an atom gains or loses 2 electrons, we call that atom divalent ion. When an atom gains or loses 3 electrons, we call that atom trivalent ion. Ions can either be cations or anions, meaning they can either be positively charged or negatively charged. Now, atoms can also have multiple variable valency or multiple valency. The two examples that we discussed was copper, which shows a valency of +1 and +2, and we discussed ferrous ion or iron being in the form of ferrous and ferric having multiple valency of +2 and +3. Valency is what helps us make a formula unit for a compound, for example NaCl or MgBr2 or Na2SO4. Then we studied how to balance a certain chemical equation. We studied that we first write the given chemical equation in the form of word if it's not given to us. We then write it in the form of symbolic representations, that is, we write the whole chemical equation. We balance the element with the maximum number of atoms, be it either on the reactant side or on the product side. We then go to the next element with maximum number of atoms and balance it and keep doing so until every atom in the equation is balanced. The last step includes cross-checking the entire equation by counting the number of atoms of each element on both sides, that is on the reactant side and on the product side. This will then complete the balancing of our chemical equation. This is what we studied in our previous session. Now, in this session, we will be studying about how we make our balanced chemical equations more informative so that they can offer more information to the person who's studying that example or studying that balanced chemical equation. Then we will study about how we can interpret those chemical equations. What will they help us calculate? And then we will study two different numericals that are based on your book that will help us calculate some kind of number of molecules or atoms of different substances from the equation using molar mass and Avogadro's number. We will make a summary of this entire session and then we will recall the chapter chemical equations. So without any further ado, let us begin. Making chemical equations more informative. There are generally four ways that we would be studying in which chemical equations can be made more informative. So, by expressing the following characters in the form of either reactants or products, the physical state of the reactant or the product can help us make a chemical equation offer more information. We will see if that state that we first made the chemical reactant was either a liquid or either a solid, and the product state that we now get of that substance is either a liquid or a solid or a gas or something else has been formed. We can either explain whether a heat change has taken place or not. It means we have to represent a reaction being an either endothermic or exothermic. Means either heat is liberated being exothermic or heat is absorbed being endothermic. If there is any gas evolved, we can even represent using arrows upward and downward to see if gas is evolved or a precipitate or a kind of residue is formed, if there is any. Let us first begin. Physical state. If you have to make a chemical equation more informative, the physical state of the substances may be mentioned along with their chemical formulae. So, the different states that we know are gaseous, liquid, solid states. Gaseous state can be represented by a small g. Liquid states can be represented by a small l. All of them have to be under brackets. And solid state can be represented by a small s. If the substance is present in water as a solution, for example, solution of sodium sulfate in water, then what we would write under brackets is AQ. AQ means the word aqueous. Aqueous means in water. Now, if a balanced chemical equation of ferric oxide being reactant with aluminium giving us iron plus aluminium oxide is written, and we have to see that heat is provided to it, and we have to mention all the physical states, it will be written as Fe2O3, which is iron oxide, that is in the solid state. So we represent an S plus 2 molecules of aluminium, which is in the solid state, react together and it gives iron, which is in the solid state, and Al2O3, aluminium oxide, which is also in the solid state. The slower small triangular symbol that is there on top of the arrowhead, it represents heating. It means heat is provided during the reaction. This is how a balanced chemical equation and physical states can be expressed together. It makes a balanced chemical equation more complete, since we now know in what form did the reactants react and in what form did we get the products. Next, expressing heat changes. Now, normally this is a more physical concept rather than a chemical concept expressing a heat change, but heat is liberated in an exothermic reaction and heat is absorbed in an endothermic reaction. Now, if we see an example that has been provided to you, carbon reacts with oxygen to give carbon dioxide, plus some heat is liberated. How much heat is liberated is not our concern as of right now. We know that some kind of heat is liberated, so it is an exothermic reaction. In addition to balancing the chemical equations and mentioning all the physical states of each element, for example, carbon being in its solid state, oxygen being in gaseous state, giving us carbon dioxide, which is a gas, so gaseous state, we have to mention a plus Q. Q is the heat energy, which when liberated is shown as in a plus sign, and which when is either absorbed is shown with a minus sign. So look through the second example, which is an endothermic reaction, where N2, which is a gas, nitrogen gas, reacts with oxygen, which is also a gas. Gives us 2NO, which is also a gas, but heat is absorbed, hence minus Q. Q is the heat energy which is shown. So if we were to represent heat changes in a given chemical reaction, we first explain the physical states of those elements, we balance the equation, and then we write either plus Q or minus Q on the product side, explaining whether the reaction that was given to us was exothermic or the reaction that was given to us is endothermic. Gas evolved. Usually, gases, when they are evolved, they travel upwards, right? Hence, when a gas is evolved in a reaction, it can be denoted using an upward arrow. In the given example where zinc reacts with H2SO4 to give zinc sulfate plus hydrogen, we see that hydrogen gas is evolved. First, we balance the entire equation and then we write that zinc is in the solid form, H2SO4 is in water, hence it's in aqueous form. It gives us ZnSO4 plus H2, which is hydrogen gas. Now, to represent that this hydrogen gas is evolved, we use an upward arrow right on the right hand side of the gas that is evolved. This completes expressing the gas evolved with the physical state, and depending on whether we have to mention if the reaction is exothermic or endothermic, it depends on the condition. Next, expressing a precipitate which is formed. A precipitate is basically like a residue that is formed after two reactants react with each other to give a different kind of product. Let us see, when silver nitrate reacts with sodium chloride, that is NaCl, silver chloride is formed as a precipitate and NaNO3, that is sodium nitrate, is formed in the aqueous form. Now, silver chloride goes in the form of a precipitate. Since it goes down and settles down, we use a downward arrow to represent that a precipitate has been formed. So, in this balanced chemical equation, we say AgNO3, silver nitrate, aqueous form, plus NaCl, which is also aqueous form, gives us, in the direction of the arrowhead pointing in the direction of products, AgCl, silver chloride, as a solid precipitate, so we put the down arrow, plus NaNO3 in aqueous form. Sometimes the reaction conditions such as pressure, temperature, or catalyst is something that helps in the reaction. It either increases the speed of the reaction or it decreases the speed of the reaction. It is something that affects the reaction, rate of reaction. That is a catalyst. So they can be indicated. Where do you indicate such reaction conditions? Right above or below the arrow. For example, if you're providing some heat, you use the triangle symbol just above the arrow to say that you are providing heat to the reactants. Or if you're providing sunlight to the reactants, or you know that carbon dioxide and water in the presence of sunlight and chlorophyll, they form glucose and oxygen. This is the basic process of photosynthesis, the second equation that has been given to you in the form of examples. So sunlight and chlorophyll, they act as catalysts and temperature conditions. So where do we mention them? Right on top and below the arrowhead. So the reaction then is 6CO2, that is 6 molecules of carbon dioxide, gaseous form, react with 6 molecules of water, H2O, in liquid form. Catalysts being and reaction temperatures being sunlight and chlorophyll give us C6H12O6, which is the formula for glucose in its solid form, plus 6O2, that is oxygen in its gaseous form. Or one more example, when silver chloride in its solid form reacts with sunlight, or in the presence of sunlight, not reacts with sunlight, in the presence of sunlight, it dissociates and it gets us just silver and chloride, both in one in solid form and the other in gaseous form. So the reaction condition is temperature or heat, which is provided in the form of sunlight. So this is how you can express different ways and make a chemical equation, a balanced chemical equation, more informative. Now, we study about interpreting a basic balanced chemical equation. We know that the chemical equation gives information about the reactants, about the products, whether they are in solid form, whether they are in liquid form, whether they are in gaseous form, whether heat was evolved, whether heat was not evolved, whether a gas was evolved, whether a precipitate was formed, whether some kind of temperature condition was changed, whether some kind of catalyst was present and was affecting the rate of reaction. But the thing is, the chemical reaction, it gives us more important information. When you try and study a basic balanced chemical equation, it will give you the ratio of molecules of reactants and products because it is balanced. We know that as molecular masses are expressed in U, the symbol U, the relative masses of reactants and products are also known from the equation. And if the masses are expressed in grams, and then the equation also gives us molar ratios of reactants and products using Avogadro's number. If gases are evolved, we can say that we can equate their masses to their volumes, and we can calculate the volumes of those gases that are liberated at a given condition. And we can see that given condition is either for temperature or of pressure, and we can calculate it using molar masses and molar volume relationship. Now, using molar mass and Avogadro's number, something that we have studied in the previous classes, we know that 1 mole of a substance contains 6.022 into 10 to power 23 molecules. We can calculate the number of molecules and atoms of different substances from an equation. This will give us information about relative masses of reactants and products. So from this balanced chemical equation, you can have a mass to mass relationship. If the mass of the reactants are given, you can somehow calculate the mass of the products if you have the right ratio. And to have the right ratio of molecules, you must always have the equation balanced. Mass volume relationship, since you know the mass of this particular reactant and you know the mass of the product, you can easily calculate volume. Now we can also calculate volume relationship. If a different volume at a certain temperature and molar condition is given to you, you can calculate the volume of the product that will be given to you. And since mass volume relationship, we can have the number of molecules relationship also, because we have the Avogadro's number to calculate it. So to interpret a basic balanced chemical equation, I have used two different numericals that were presented in your book. This will give you a better idea of how these relationships are maintained and calculated. So the given equation to us is aluminium Al plus Fe2O3, that is ferric oxide, reacts in some presence of some catalysts, and it gives us Al2O3, that is aluminium oxide plus iron. The atomic masses of aluminium is 27 unified mass. The atomic mass of iron is 56U, and the atomic mass of one oxygen atom, and not O2. The atomic mass for O2 or the molecular mass of O2 is 32. One oxygen atom has an atomic mass of 16 units. So we have to now calculate the mass and add them according to the equation. So we have the equation as 2Al, balanced chemical equation as 2Al plus Fe2O3 gives us Al2O3 plus 2Fe. Let us check if it's a balanced equation. Let's first take aluminium. We have two atoms of aluminium on the left hand side, and we have two atoms of aluminium on the right hand side. Let's check iron. We have two atoms of iron on the left hand side, Fe2, and we have two atoms of iron on the right hand side, 2Fe. We have three atoms of oxygen on the left hand side, O3, and we have three atoms of oxygen on the right hand side, O3. So this entire equation is balanced. So let us now calculate the masses. We have two atoms of aluminium. So 2 into 27 gives us 54. Fe2O3, we will calculate the mass of Fe, and we will calculate the mass of oxygen atoms and add them together to get the mass of the compound Fe2O3. So iron or ferric has a mass of 56. Two atoms are present, so we multiply it by 2. 2 into 56 plus we have oxygen as its atomic mass being 16. We have 3 atoms, so we multiply it by 3, giving us 3 into 16. We add the entire masses, and the total mass we get of ferric oxide compound is 160 units. Now let's calculate the masses on the product side. We have Al2O3. So we have 2 Al atoms, right? 27 into 2 plus 3 into 16. Since oxygen has atomic mass of 16. The total mass that we get for the compound Al2O3 is 102. Let us now calculate the remaining mass, that is Fe. Fe again has a mass of 56. 56 into 2 is 112. Now, you have now calculated it in unified mass. So now we will see that 2 moles of aluminium plus 1 mole of Fe2O3 gives you 1 mole of aluminium oxide plus 2 moles of Fe. Or you can say that 54 grams plus 160 grams gives you 102 grams plus 112 grams. This is something that you can already calculate just by having the atomic masses, right? Now, the question that is posed in front of you is that you are asked to calculate the amount of aluminium required to get 1120 kgs of iron by the above reaction. So, we have to calculate some amount of iron when we have some amount of we have to calculate some amount of aluminium while we have some amount of iron. So already we know that 54 grams of aluminium gives us 112 grams of iron. How? We calculated it using our equation. So from the equation you see that 2 moles of aluminium gave us 2 moles of iron, right? So 54 grams of aluminium gave us 112 grams of iron. So 1 gram of aluminium will give you 112 by 54 grams of iron. So x grams of aluminium will give you 1120 multiplied by 100 because we are calculating in grams and not in kgs. The mass that has been given to us is in kgs. So 1120 kgs times 100 times 1000 into grams into 54 divided by 112. 1 gram of aluminium will give you 112 by 54, but 1 gram of iron will give you 54 by 112 grams of aluminium. What we have is iron. Hence, x grams of aluminium will give you so and so iron. So that x grams is equal to 1120 multiplied by 1000 multiplied by 54 grams divided by 112 grams of iron. So after we get 5,40,000 gram or 540 kgs, we can write our answer as to get 1120 or 1120 kgs of iron, we have to use 540 kgs of aluminium. This is a basic numerical that can be done by unitary method. We already know, since I will try and explain it again, 54 grams of iron gives you 54 grams of aluminium gives you 112 grams of iron. So 1 gram of iron will give you 54 by 112 grams of aluminium. This is unitary method. So to get x grams of aluminium, you will say 54 by 112 multiplied by 1120 kgs. That kgs you will need to convert into grams. That much aluminium is the amount of aluminium you will get when you have 1120 kgs of iron. So this is it for this example. Let us now go to the next example. We have to calculate volume, mass, number of molecules of hydrogen that is liberated when 230 grams of sodium reacts with excess of water at STP. Now, STP is standard temperature and pressure. Standard temperature is 273 Kelvin and standard pressure is 1 bar, something that you don't have to worry about right now. Now, the balanced chemical equation for the given word equation for us is sodium reacting with excess of water. So when sodium reacts with excess of water, it produces sodium hydroxide plus hydrogen gas is evolved. We have balanced the equation when we were studying balancing of chemical equations. So we know that 2 molecules of Na react with 2 molecules of water to give 2 molecules of sodium hydroxide and 1 molecule of hydrogen gas. So to calculate the basic masses, we have 2 molecules of sodium. Atomic mass of sodium is 23. 2 into 23 gives us 46. Now, to calculate the entire mass of the H2 molecule, we will say 2 into 1 for hydrogen, since the atomic mass of one hydrogen atom is 1, plus 1 into 16, since we have only one atom of oxygen. The entire bracket, we will multiply by 2 since we have 2 molecules of water. So the atomic mass of the entire molecule is 18, multiplied by 2 gives you 36. Let's come to the product side. We have NaOH. Na, we have one molecule, so that is 23. Oxygen, we have one atom, we have 16. And hydrogen, we have one atom, so it's 1. 23 plus 16 plus 1 multiplied by 2 gives you 80. Now we have one molecule of hydrogen gas, but we have two atoms of hydrogen in one molecule of hydrogen gas, right? Two atoms of hydrogen in one molecule of hydrogen gas. Hence it is 2 into 1, that is 2 units. So we say 46 grams of sodium with 36 grams of water molecules gives us 80 grams of hydrogen oxide, that is sodium hydroxide, plus hydrogen gas 2 grams. As per the balanced equation, we can see that 46 grams of sodium gives us 2 grams of hydrogen, right? So all we have to see is how is 1 gram of hydrogen given. 1 gram of hydrogen comes by 46 by 2, right? Or so and so molecules of hydrogen will give you 46 grams of sodium. So 230 grams of sodium will give you how much amount of hydrogen? That will be 230 multiplied by 2 divided by 46. This is a basic unitary method. Doing the entire numerical will give you 10 grams of hydrogen. Now we have the mass. We know that 1 gram molar mass of any gas at STP, that is standard temperature and pressure, occupies 22.4 liters volume. That is 1 gram molar mass. 1 mole at 22.4 liters occupies 22.4 liters of volume. This volume is called molar volume, volume of 1 mole. Now we know that 2 gram of hydrogen occupies 22.4 liters at STP, because 2 gram of hydrogen is what is 1 mole in this given equation. So 2 grams of hydrogen occupies 22.4 liters at STP. So 10 grams of hydrogen will occupy how much? Basic unitary method will give you 10 grams multiplied by 22.4 liters divided by 2 grams, which is 112 liters. So we know that 112 liters is how much 10 grams of hydrogen will occupy at standard temperature and pressure. 2 gram of hydrogen, which is 1 mole of H2 from the given equation we got. So we know that 1 mole or 2 grams of hydrogen will contain how many particles? That is 6.02 into 10 to power 23, Avogadro's number. So 10 gram of hydrogen will contain 10 multiplied by the number of Avogadro's constant divided by 2 grams. That will give you 30.1 into 10 to power 23 molecules. If you were to convert it into standard form, you shift a decimal by saying 3.01 into 10 to power 24 molecules. Again, 2 grams of hydrogen from the given equation is how much 1 mole of H2 is in this given equation. So 1 mole of H2, we know 1 mole of any substance, be it any amount, contains 6.02 into 10 to power 23 molecules. Now we have 2 grams containing these many molecules. We have to find for 10 grams. We use unitary method. We will first find the number of molecules for 1 gram, and after we have for 1 gram, we just multiply it by 10. Basic unitary method will help you calculate most of these masses, volume, number of molecules easily. We will discuss some more examples when we come to exercises for this chapter. What is most important is that the equation that you write must be balanced. If the equation isn't balanced, the masses that you will calculate will go wrong. If the masses that you calculate will go wrong, all your answers will go wrong. Hence, it is important to balance this chemical equation, any that is given to you, or it is important to check whether the equation is balanced or not. That is it for this session. Let us now discuss what we studied. We know that chemical equations can be made more informative by expressing some characteristics. So we can express the physical state, that is either it's in liquid, it's in solid, it's in a gaseous form, or it's in aqueous form, by writing small case letters for solid S, liquid L, gaseous G, aqueous AQ inside brackets. If we were to express heat changes, if it's an exothermic reaction, at the end of the product you write plus Q. If it's an endothermic reaction and heat was absorbed, then you write minus Q. If there was gas evolved, if any, you write it using an upward arrow and the G symbol. If a precipitate was formed, then you use a downward arrow to represent that this molecule or this compound has been formed in the form of a precipitate. Next, we know our chemical equations give us information about reactants and products through their symbols and formulae, but it also gives you ratio of molecules of reactants and products. Now, from the unified masses, you can calculate relative masses, and from the relative masses, you can actually build relationships between your reactants and your products. If the masses are expressed in grams, then the equation will give you molar ratios of reactants and products. Hence, from unified mass, we generally convert it into grams. Now, if gases are evolved, we can equate their masses to volumes and calculate the volumes of those gases that were liberated. Okay, next, using molar masses and Avogadro's number, as we know 1 mole of any substance contains 6.02 into 10 to power 23 molecules. We can calculate the number of molecules of atoms of different substances from a balanced chemical equation. It will give you information about relative masses of reactants, of products. So you can get a mass-mass relationship, a mass-volume relationship, a volume-volume relationship, a mass-volume and number of molecules relationship. Because if the mass is expressed in grams, we can express it in the form of molar forms, and from molar forms we can get to number of molecules. That is it for this session, and that is it for the chapter chemical equations. Let us recall what we studied in the entire 3 sessions of chemical equations. We were saying that a change that takes place in our environment is broadly classified into 2 types. Physical change, where no new substance formation takes place, or a chemical change where new substance is formed from pre-existing ones. You know that when a chemical change takes place, either that chemical change turns out to be endothermic or exothermic, means either heat is absorbed or either heat is liberated. In a chemical reaction or a chemical change, a change in state of the reactant may be caused. There may be change in color or other characteristics may be involved. Even though most chemical reactions take place and new substances are formed, those substances that are formed may lead to a formation of precipitate, like a residue. We know that when 2 reactants combine with each other, a certain kind of product is formed. This is exactly a change that is taking place. This change is called a reaction. Now, the symbolic representation of a chemical reaction, when you use the chemical formulae of the compounds and the symbols of elements that are involved in the reaction, then this process will be termed as a chemical equation. Elements that undergo the reaction are called reactants. They come on the left hand side, and those that are formed are called products. They come on the right hand side. We form an arrowhead to direct to the point where the products are being formed. Chemical equations all obey law of conservation of mass. It means during a chemical change or during a chemical reaction, heat is neither created, mass is neither created or mass is neither destroyed. Hence, the number of atoms of each element on the reactant side must be same as that on the product side. Equations need to be balanced. We know that mass can neither be created nor mass can be destroyed, and that is the concept that is used, and why we need to balance chemical equations is understood. Before we start balancing chemical equations, we understand the concept of valency, that is the combining capacity of an element. An element either gains electrons or loses electrons to become a positively or a negatively charged ion, and those ions then combine with each other to form different kinds of compounds. Elements can be monovalent, elements can be divalent, elements can be trivalent. Means they can either lose 1 electron or 2 electron or 3 electron. There are some elements that show variable valency, for example copper and iron. Valency helps us make formula units for compounds. To balance a certain chemical equation, we write the chemical equation first. We balance the element with the maximum number of atoms either on the reactant side or on the product side, it does not matter. We go to the next element with the maximum number of atoms and keep doing so until the whole equation seems balanced. Last step includes cross-checking the entire equation by counting the number of atoms of each element on both sides. We know that after we have balanced an equation, we can make this chemical equation more informative by expressing some different characteristics of the reactants and products. One of them is physical state, whether it's a solid, liquid, or a gas. We can express heat changes, meaning we can express whether the reaction that just took place was an exothermic reaction or an endothermic reaction. We can express from an upward arrow whether a gas was evolved. We can express through a downward arrow whether a precipitate was formed. So, a chemical equation gives information about the reactants and products through symbols, formulae, and through different characteristics that we express. Usually, if molecular masses are expressed in unified mass, then the relative mass of reactants and products are known. This can be converted into gram mass that are expressed in grams, and then we can calculate molar ratios of reactants and products. If gases are involved, we can equate their masses to their volumes to calculate the volumes of those gases that are liberated at a given condition of temperature and pressure. Using molar mass and Avogadro's number, we calculate the number of molecules of atoms of different substances from a balanced chemical equation. It gives us information about relative masses of reactants and products. Then from the equation that we just balanced, we get a mass-mass relationship, a mass-volume relationship, a volume-mass relationship, a mass-volume number of molecules relationship. It is important to balance that chemical equation because if you not, the number of numericals that you will do when you will calculate different masses will go entirely wrong. This is all for the chapter Chemical Equations. We will meet next when we discuss the exercises that are related to this chapter. Till now, this is it. Thank you and please be safe.